Okay, Unit 3. This unit talk about logic statements, and truth table. Okay, what is meant by a logical statement? A logical statement or short statement is a proposition by which it's possible to decide whether it's true or false. There is no ambiguous interpretation. Example, if say x is an odd number, we can say it can't say if is a statement because we don't know the value of x, and it can be also true or false. So this is not any statement. But if we say 4 is an even number, this is a statement and the logical value is true. Atomic statement is a statement if it cannot be divided it in smallest elements. Example, if we say 4 is an even number and belongs to the natural set, there are two parts we need to analyze: if 4 is even and if 4 is natural. This is not atomic statement. Atomic statement, we only analyze one thing by time. To transform this in an atomic, we need to say 4 is an even number and 4 is a natural number. Okay, what's the logical equivalence of statements? Logical equivalence of two statements, if they have the same truth value. Example, if both are true or both are false. To say they have the same truth value, we use this sign. 3 lines. Example, 7 is an odd number. This is true. It's dark at night. This is also true. So we say this A is logical equivalence to B. But we say this is not the same of this. Here we are talking about number. Here we are talking about the night. So this is not equal because there are different things being analyzed here, but they have the same truth value. So we can say there are logical equivalence. The statements are different, but the contents don't. But so A is different than B, but they have the same true value, so they are logical equivalence. Let A and B be statements with A is equal to 2 is a number and B, the sun is bigger than the moon. Are A and B propositionally equivalent? Yes. The equivalence relation is about the truth value. 2 is a number. This is true. The sun is bigger than the moon. This is true. The content is different. Okay, but the logical equivalence is true. Then A is logical equivalence to B. What is a logical operator? Also called connectives. Logical operator is also called connectives. Okay, can be used to combine logical statements. By this combination, the results the name of the name is a propositional formula or expression. Okay, we got a proposition, we use the connective or a logical operator, and it results propositional formula or expression. Okay, always first we do the negation, then the conjunction, disjunction, conditional, biconditional. This is the order. Negation is the not. Conjunction is the and. Disjunction is the or. Conditional, if, then. Biconditional, if and only if. É o if. Negation, not. This is to construct the true treble. So, negation. Negation will only reverse the true value. So, if it's true, becomes false, and if it's false, becomes true. Conjunction. Conjunction is the and. Both must be true should the conjunction be true. Conjunction and only accept true. So, A conjunction B, the true table, false, false, false. True, false, false. False, true, false. True, true, true. Disjunction or. The or, we need to have at least one true. If we have one true, then it's true. False, false, false. No true here. True, false, true, because we have true. False, true, true, because we have true. True, true, true. Okay. Implication or conditional. If, then. Will be will false only when A is true and B is false. Is the only conditional to implication be false, because we can't have true and get a false result. But if we have false, false, we can get a true. If we have a false and a true, we can get a true. True, true, true. A true and then a false, it don't. So, false. Biconditional. Biconditional is a double implication. Is the if. Both statements must have the same logical value to be true. So, must be equal. If and only if. False, false, then true. True, true, then true. All others are false. There is an order to resolve the logical operator if there is no brackets. If we have brackets, we use the brackets, but inside the brackets, there is an order. First, not, then, and, or, if then, if. To solve propositional formulas, you must follow this rule. How propositional formulas are defined? The logical statement can be combined with logical operators, okay, not, and, or, if then, if. Interpropositional logical formula, also called propositional logic expression. A and B. Okay. This can be abbreviated. A and B can be abbreviated. When it's written together like this is and. So we can abbreviate it as not A, and B. So AB or C. What true tables are and how to work with them. Truth tables are a tabular tool for determining the true value of propositional formulas, being very helpful in determining the true value for complex propositional expressions. Write down in a truth table. Each column represents of a propositional formula under consideration. For each possible combination of the value assigned of the operation, this is a line of the table. Let A and B be statements. Plot the truth table for the expression A or B. Any or, remember, or any positive, then positive. A, B, make like this. Not, true, not, true, true, true. Then, any positive, then positive. Not, true, true. One true, true. Both true, true. Let A, 4 is an even number, and B, C is an odd number. Check whether A and B and A or B are true or false. A is true, B is false. So A and B is false because conjunction needs two values true to be true, and B is false. A or B disjunction is true since at least one of the statements is true. In this case, A is true. Let A, 4 is an odd number, and B, 3 is an odd number. So A, if A, then B. And if B, then A are true or false. A is false, B is true. Let's remember. If then, we need to be false. We need to be false. We need to start with true and end with the false. So A then B. A is false. This is true because A is false statement and false statement. Everything can follow. Okay. B then A is false because B is true and A is false. And from a true statement, a false can't follow. What is equivalent to? Save as many brackets as possible considering the binding strength of the operations. Okay. We can't put out these brackets because this is an and is stronger than or, and if we take it out, this will make A and B first, and this is different, so we can't put out these brackets, only put the sign upper A. Let A, B, C be statement. Plot the truth table for the expression. Okay. We make the truth table. All combinations. True, 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 true. Okay. B, C, and must have two true. Should be true. So B, C. Only these two are true. Agora, now A and we need two true to be true. So only this. Define tautology. A statement or formula that is true in every possible sense. Can be a statement or formula. Okay. Is known as a tautology. A propositional logical expression that is always true regardless of the assignment. Regardless of the assignment of the variables occurring in it's called tautology. Example, let T true, then T is a tautology because T is also true, always true. Example, propositional expression, not A union A is a tautology. Union don't, or, not A or A. Or if we have one true, then true. So A, not A, true, true. Okay, tautology. Determine contradiction. A propositional expression that is always false, regardless of the assignment of the variable it contains. Example, false. False is false. Always false, then contradiction. The expression A and not A and must have two true to be true. So, no true, always false. If the following a tautology, so first we make A, not A, not A, we come back to A, if and only if A. It's a tautology. Because 0, 0, if and only if need to have two equals to be true. Equal, equal, true. Equal, equal, true. Let A, B, C be statements. Create a truth table of the following expression. Okay, we make A, B, C, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, ta-ta. Okay. First bracket, write down. Not C, write down. Second bracket, write down. And the union between the two brackets. Union and 0, 0, 0, 0. And must have two true to be true. No, true to be true, yes. The only true, it is. So This is not a tautology and not a contradiction. Computational rules of propositional logic. Theorem: rules of calculation of propositional logic. Let PQR be logical expressions. Okay. Associative rules, associative laws. And it's the same of the sets. Associative is the same logical value. Same logical value. Commutative. Pay. This is interesting. The same. You can change the position, but it's the same logic. Distributional is the same. P and Q, P and R, or the same of the sets we studied previously. P union Q, P union R, and Morgan. The same Morgan. Yeah. But instead of the sign of not, we use this not. P, not. Is the same, and not P union or not key. Generalization of the laws of Morgan. Generalization. If we have many, then many. Okay. Let PQR be propositional expressions. What are the associative laws? The associative laws of PQR. Okay, is this. Associative, commutative, distributional, Morgan. ACDT. Associative, commutative, distributive, Morgan. Let P and Q be positional statement. Prove the following commutative. It's just proof. It's the same logical value. Okay. Let P and Q be propositional statements. Prove the Morgan second law. Not P or Q is the same logical value of not P union and not Q. True, false, true, false. It's the same. Let P be a propositional statement. Prove the identity of the disjunction. Identity of the disjunction? Disjunction here. Strange. According to which principle can propositional statements be simplified? Replacement principle or substitutional principle? With the calculation rules and the logical equivalence presented so far, we can simplify propositional expression by replacing variables contained in them consistently Example, by identical expression. This is a proven tool to make complex formulas easier to understand without. This is called the replacement principle or substitution principle. Both are the same. Let P and Q be propositional expressions. Simplify the following formula. As much as possible, applying the calculation rules. When the exercise say apply the calculation rules, use the truth table. The truth table can show you some points are equal, so you can exclude this point. P and not P and Q is logical equivalence. P union not P union Q. It's the same. The exercise gave me this. I don't know. Key. Don't get it. P and not P. Oops. P 0 not P 0 1 and must have true to be true. This is 0. Okay, now I got it. This is 0 0 and key. 0 and key. Key 0 0 need true to be true, then all false, then all this is false. Okay, now I get it. Simplify the following formula as much as possible. A and A or not A. Make the distribution. Okay, and A and A, and it's A. Okay, or A and not A. A not A. And true to be true, then this is 0. Is equal to A or 0. A or 0. The same value of A 1 0 0 0, or if one true, then true. True, the same of A. Okay. Simplify the following formula by applying the calculation rules. P union don't, or P or Q and not P. Okay. P not P. first? The distribution, and this distribution. P intersection, union, union. Okay, now I got it. Not P and P, not P and P, not P and P is 0. This is 0. Or this. This can be eliminated because or don't change the value, maybe it's it, or negative, don't change the value, so you can eliminate. Okay, it's the end of the unit 3.